Hello everyone, welcome back to my channel. Today we are going to begin our simulation using Ansys Workbench, and in this tutorial we are going to use Ansys, and we're going to analyze a steel plate with a central hole. As you can see, this is the plate we are going to simulate. We are going to first sketch it as we've been seeing in our previous tutorials. Then we shall simulate to determine the maximum stress on this plate. As you can see, the plate is loaded along direction along the x direction, by a tensile force of 400 newtons, and its dimensions are given as below. So we are going to begin right away. We are going to sketch, and today we are going to look at a static structure. This is a static structure which are going to load, apply the forces. However, we're going to begin by sketching as we've been seeing in our previous modules. So the engineering data, of course, the default is steel, so we're not going to set the engineering data. Geometry, we are going to set the geometry, and going to use the design modular as always. So our plate, we have the dimensions given, 500 from the center, and 1000 long, 400 meters high, and with the thickness of 10 millimeters. So the first thing, as always, is to change our units. We are working in millimeters. We are going to sketch on the XY plane, so we can do this very fast. Go for sketching. Going to use a rectangle. Then I will center this rectangle by symmetry. Then along the horizontal axis. Then we shall dimension our rectangle, our rectangular plate. It is 400 high and 1000 long. So horizontal is 1000 millimeters and vertically is 400. So we can fit it. So this is it, and 4 millimeters and 1000 millimeters long. Then a thickness of 10 millimeters. So we can go back to our modeling, put it back in isometric. We can fit it a little bit. Then we can extrude. We are extruding on our sketch, so it selects the whole sketch, and we can apply. So when we apply, we are going to leave our direction to be normal as it is. We are not going to make it symmetrical. Then it is 10 millimeters. 10 millimeters, then we can generate. Okay, so that is our steel plate that we've constructed. Then we have a circular hole in the center of 200 millimeters in diameter. So we can draw this also. So you can sketch this on this plane. We can either create a new plane or we can sketch it on this front plane. So to do this, you just click on the plane. You will see the green highlight. Then you go back to sketch. Then you can you can face it your side. So we are sketching on this plane. So it means a new plane has been created. When you click on a face, Ansys is very good, or is better than other softwares in a way that it creates a plane automatically. However, there is a process of creating a plane wherever you want it. We shall see that as we continue with our tutorials. So we need a circle. Put it anywhere. Then we can center this circle. We were given 500 from this side and 200, so it is centered. So we can dimension it. This is horizontally, and same time can go for the vertical distance like this. So horizontally it is 500. We need it in the center. Then vertically it is 200. Okay, so we can go back to our modeling, put it back in ISO. Okay, so I can fit it a little bit such that you can see, can fit it. So our circle is in the center. As you can see, it has been centered. So we are going to cut out to have the hole. So still you go to extrude, then we are on this plane, the new plane, as I told you, it has been formed automatically. Click on the sketch and we apply. So in apply, you can see the blue highlight on our circle. Then in the other case of extruding, in the first place, what we did to form this rectangular plate, we added material. So the operation is now we are going to remove material, we are going to cut material. This extrusion bit has a lot of things you can do with it. You can slice material, imprint, as you've seen earlier, and we shall continue seeing it in details as we do different projects. So we are going to cut out material, and material, you see, it is automatic in a way that it has selected reverse, because to remove material, it cannot be normal. So it has reversed the extrusion to be from the other side. As we saw extrusion in our previous module, it can be reversed, it can be symmetric, it can be asymmetric, it can be normal. So Ansys uses that artificial intelligence to extrude cutout. So it is reversed, and the extent you can make it fixed, or you can say through all, or you can say to next surface. But here I don't have a lot of surfaces, so I can say it is fixed, or I can say through all. Then I can generate. So as you can see, our hole is formed. Now we are done with our geometry. We can continue to simulation, or you can simulate it as a full plate, but as long as the geometry you're dealing with is symmetrical, it's always advisable to use symmetry. Now, what is the importance of symmetry? Symmetry is going to help you in the first place, the runtime for your simulation, and your CPU time. So it's going to save you a lot of time by analyzing a single portion of this plate instead of running the whole plate. So in this tutorial, we are still going to learn how to apply that. So I can use a portion of this plate just to simplify my work, because this plate is symmetrical as it is centered and the hole is centered. So you can come to tools and look for symmetry. So when you go for symmetry, it's going to ask you how many planes do you want. So I want to use a quarter of this plate, and what I'll do, I'm going to cut using the XY plane, and then I'll cut again using the XZ plane. So the number of planes here, it will ask you the number of planes. Number of planes, it will say not selected. Then you say I'm going to use 2 because I'm going to use a quarter. Then the first plane, as I've said, I'm going to use this plane. I'm going to use the YZ plane to cut it. That is YZ plane. Then I apply. Then the second one, I need to cut it horizontally, so I'm going to use the ZX plane. So I'll select the ZX plane. That's the second plane. Then I say apply. So after apply, you just click on generate. Now you can see this is the quarter I'm going to use. Now this will represent the entire model. This is the most important thing about symmetry. You don't need to make the whole plate. You just, as long as what you're analyzing is symmetrical, you can just analyze a portion of the plate. So now we're done with our geometry. We can go back, continue with simulation. Now, simulation, it's where we are going to define the loads, the boundary conditions, and you'll just need to right click and go for edit. Okay, so the workbench simulation environment has the same, almost similar aesthetics with what we've seen in our work modular, design work modular. It has the tree on this side, the tree that has the model. It has geometry. It has material, it has mesh, it has the environment, and it has the solution. So the first thing, you can still check your units and see metric, we're in millimeters. So I can turn to millimeters. Then the other thing is the material. We have to assign the material. In our question, the material is a thin steel plate. So we are going to continue using structure steel. What you do, open your geometry, go to your solid model. You see it is highlighted when I click on it. Then come to material. So you can set a lot of things. And of course, as in our introduction module, when you're talking about assigning material, we said structure steel is the default by Ansys. But if you're dealing with a different material, you can create a new one, and we saw how to create that in our first module. If you haven't checked it out, please check it out. You can import and you can edit this structure steel, because steel has plenty of kinds depending on the carbon concentration. Okay, so the material is steel. Then we can go for meshing, because you can see everything is represented. After knowing the material, now you can also come here and click on the material to know which kind of material. You see it highlights and say it is structure steel by default, which is this one. You can still change it if you want to change. You can by right clicking. Right click, it says create material or assign a new material. So with that, still we can see the coordinate system, because we are dealing with the global. Our symmetry axis, they are being shown, region 1 and region 2. So you can see this dot is showing you the first symmetry is here. Then when you click to the second one, the second symmetry is also shown. Then we can go to meshing. So to mesh, as we said, finite element analysis, meshing is an integral part of our analysis. So to create a mesh, we are going to see we have different kinds of meshes. We're going to break down this component into finite elements. So you can right click on mesh, then you say generate mesh. So it's going to generate a mesh, a default mesh. So this is a default mesh. As you can see, it has broken it down into elements of thickness. You can see the thickness is the 10 millimeters we put in. You can make this finer, as we shall see when we learn how to improve mesh quality. We shall see that. So after meshing, you can improve the mesh, and when you come down here, we have the sizing. You can improve the sizing, you can improve the quality, the inflation. Inflation means where exactly you want to concentrate more, or where you want to put more finer meshes or larger meshes. So you can go to statistics. When you go to statistics, in statistics, we can know the number of elements and the number of nodes. So when you look at this, the number of elements is 114 elements, and the number of nodes, there are 931 elements, nodes. So these are brick elements, as you can see them. So if you want to make it finer, we shall see how to do that, how to improve. Since this is our first analysis in simulation, we're going to be looking at plenty of things. After that, we go to structure, static structure. Now in this section, we are going to define the boundary conditions, and we're going to apply loads. So in the question, we can see that the plate was loaded along we can see that the plate is loaded in the x direction and with a tensile force of 400 newtons. So we shall begin by applying the force first. So you come to static structure. You have two ways of doing this. The first way, you see here we have inertia, and we can check we have acceleration, gravity, rotational velocity. We have the loads. We have the pressure, hydrostatic. We have force, to mention but a few. Then we have boundary conditions, where we have fixed supports, displacements, frictionless supports. We have the conditions. So you can just come up on this bar and select what you want to apply. So I'll use this bar and say, let me first apply the tensile load that I was given. It is a force, and we're going to apply it here. Ensure you have to monitor the filters. These filters here show what to be selected. You can see this one is for the face, this one's for the edge, and this one's for the point or the vertex. So the face has to be on because in our question it is loaded in the sides. Then we can click apply. When you say apply, you can see the force is being applied. Then the magnitude of the force, it is 400 newtons tensile force. So it is a 400 newtons. So 400 newtons. Press enter. So you can see it is illustrated that it is tensile. It is pulling apart. This is giving you the direction. Then the other thing is, if it was a compressive force or a compressional force, we would have put in the negative x direction. That would be it's a negative force. Then after that, we can apply the boundary conditions, but still don't forget that we are operating on the symmetry. Symmetry, since we are dealing with a symmetrical plate, symmetry requires that we constrain the perpendicular displacements to the symmetrical planes. Remember, we have two planes. We have this plane and this plane. So we are going to apply boundary conditions to both symmetrical planes. So we shall deal with the first one. You click on it, you can turn such that you can see it better. Then we can apply. So we constrain the perpendicular direction. So it means for this symmetrical part, we are going to constrain the y displacement. So we come to the y displacement and make it 0, such that we don't have displacement in the y direction, because this is part of our plate. So we don't need movement in that direction. Then for the second symmetrical plane, which is this side, we also do the same. We shall constrain x direction to 0. Then similarly, we are going to constrain the xy plane, that is the back side of our model, and we shall constrain the z direction to be 0, and this boundary constraint helps us obtain it helps us restrain our body such that we have a rigid body motion instead of a rigid body movement, and we can only get elastic deformation when we apply this boundary condition. So we are going to restrain the displacement on the xy plane, so which is the back side. Remember, we constructed on this plane, so we shall make the z direction 0. Okay, so that is it. So now what you need, you can cross-check all your constraints. You can click on control to see that all of them are applied. So as you can see, we have the force, we have displacement constraint on the symmetrical axis, we have another displacement shown as C, and we have the last constraint. So finally, to complete our model, we need to specify the results that we need, the quality that we need, and the quantity that we need. But in this problem, we are more interested in the stress in the x direction. So to obtain that, we shall come to the solution. You right click, then we say insert. So since the stress in the x direction, you can see we have plenty of stress analysis. So we are going to go for normal stress. That is the stress in the x direction. You can add as many as you want. You can add the deformation. Yeah, I can add the deformation. Still, I can add it from here. The directional deformation. Then still the normal stress, or you can change the orientation. The orientation is in the x axis, since we are more interested in the normal stress in the x direction. Then we can finally solve. So still solve, you have this icon up, or you can right click and you have solve. So we can solve. So you can take a look at our results for the normal stress and the directional deformation, but I'm more interested in the normal stress. You can still have a simulation of a few seconds to see how deformation occurs on the plate. And the other thing, you can see the maximum stress. The maximum stress occurs at this point. Maximum stress occurs at this point, and it is defined as 1.134 megapascals, and the minimum stress is also given, and the average stress. That is the tensile stress, or the maximum stress in the longitudinal direction, that is the x direction. So you can see the quality of the mesh that we used, because the mesh usually helps to define or helps us specify the quality of our results. So you can still improve the mesh by making it finer. Then the other thing, before we leave this tutorial, you can still, as I've talked of making the meshes finer, we can add in something else that can help us identify the areas that require mesh improvement. So you can come back to insert. It's what we call the stress error. So the stress error is going to help you, because the stress error estimate is going to help you identify those elements that require to be improved for better results. And this helps us to identify the regions of high error, and the model would benefit from a more refined mesh in those areas. So after putting it here, we can solve again and see those areas. So now you can see maximum error is on these elements, and these blue elements, they have the minimum error, so you cannot refine them. You can leave them as they are to improve on your CPU time and processing time. We can only make a finer mesh in this area. So this is going to help you when you're dealing with complicated or complex geometries. It will help you identify where you need to improve for better results. So that's all for today. Thank you very much for watching. Please subscribe, and hope you've enjoyed the video. See you next time. Ciao.